म्यूट कर, म्यूट इधर, हाँ म्यूट कर, म्यूट सॉरी।
Good evening. Today we'll start with a new unit, and that is about voltammetry. So, in this unit, we will be talking about different types of voltammetry and the various methods and their potential uses. So, first is we'll begin with the basic definition of a voltammetry. So, voltammetry is the general name of an electroanalytical method where the current is measured as a function of the potential that is applied to it. So mostly voltammetry is a IE curve, that is current versus potential plot. So this is the basic working principle of a voltammetry. So voltammetry has been developed from polarography. Polarography is a particular case of voltammetry where a dropping mercury electrode it is used as the working electrode. So voltammetry it includes all the techniques where current potential measurements they are done. So we know that the measurement of current is done when complete concentration polarization it takes place in an electrochemical cell. So voltammetry has been developed from polarography, and we will be discussing about polarography in the next unit. So we can say that the electrochemical method in which the current is measured as a function of the potential applied to a microelectrode is known as a voltammetry, and if it is applied to a DME, that is dropping mercury electrode, then it is called as polarography. So other form of working electrodes are hanging mercury dropping electrode, static mercury dropping electrode, thin mercury film electrode, glass carbon electrode, or carbon paste electrode. So these are some of the working electrodes that is employed in voltammetry. So now coming to the general process of voltammetry. So various methods are assigned to voltammetry and polarography. So voltammetry is widely used for the quantitative analysis of very trace metal ions, even at the micro level. So it is a very versatile process, and it is used in the fields of redox reactions, electron transfer mechanisms, adsorption processes, corrosion proof materials, new electronic processes, and production of new types of batteries. So these are some of the potential areas of applications of voltammetry. Now, more recently, voltammetry has also been used in the production of novel pharmaceutical materials, and with the help of the with the use of green chemistry. So this is how voltammetry is used. Here in figure 7.1, some of the common microelectrodes of that is used in voltammetry has been shown. In figure A, it is a disc electrode. In figure B, it is a mercury drop electrode. Figure C, it is a hanging mercury drop electrode, and figure D, it shows a static mercury dropping electrode. So these are some of the working electrodes that are they're used in voltammetry. So now here coming to some common voltammetric methods. There are various voltammetric methods, but some of the common voltammetric methods that use are: the first is the direct current methods, second is the pulse methods, third is the stripping voltammetry, so and fourth is the alternating current method. So in the DC method, there are also four subdivisions. One is DC polarography, second is linear sweep voltammetry, third is sample DC polarography, and the fourth is hydrodynamic voltammetry. In the pulse method, it is also further subdivided into normal pulse voltammetry, differential pulse voltammetry, square wave voltammetry, and cyclic voltammetry. Then coming to stripping voltammetry, it is again divided into anodic stripping voltammetry, cathodic stripping voltammetry, and adsorptive stripping voltammetry. And the fourth one is the alternating current methods. So then we will talk about the direct current methods. So under this category, linear sweep voltammetry and hydrodynamic voltammetry is discussed. So first we will start with LSV, that is called as linear sweep voltammetry. So this is the simplest type of voltammetry that we can come across. In this technique, the potential of the working electrode, it is varied as a function of the time as the current response be recorded. So the scan rates are very slow, so that this allows the movement of the analyte to reach the electrode. So let us consider a normal reaction: A plus electron forming B, and it obeys the Nernst equation. So here E is the potential of the working electrode and E0 is the standard reduction potential of A. So if we take a solution of that contains A and we apply the potential, certain potential, then a very minute amount of current will flow into the cell and convert A to B, so that we follow the Nernst equation is followed here. The amount of current, it increases as the potential reaches the E0, that is when E becomes equal to E0. So at this point here, half of the total A reaching the electrode is converted to B, so that the current is halfway to its limiting current. So here we see, when we plot this graph, we see in that is shown in figure 7.2, this is the potential versus time plot, and it shows from the slope of this graph, which gives us delta E by delta t. The t is the time. So another important feature of this technique is that the large change in the slope around E0. So here the value of the potential corresponding to the point where the current is exactly half to that applied is called as half wave potential, or we call it as E half. So when we know this E half value can be widely used in detection of even very trace amount of metal that is present in our solution. So here, when using this E hub value, we have a term that is known as the limiting current. So limiting current will be, that is given as we have a term that is diffusion current. So diffusion current is directly proportional to the concentration of the analyte. So finally it gives id, that is the diffusion current, is equal to k into ca. And this figure 7.3, it shows the current versus potential for, this is the voltammogram for a LSV. Here we can see the polarographic determinations with higher sensitivity can be achieved if we, the ratio of the IF by IC is increased. Now in normal DC polarography, the electrode area, it is not constant, and hence the current, it fluctuates. So here we can see from this figure 7.3 how the current fluctuates. If the current fluctuates, then we can see there is a drop in the plot. So this problem, it can be solved by measuring the currents at one time, and this process is called as sampled DC polarography or test polarography. So now coming to sample DC polarography. So in this technique, instead of recording the current continuously, so we sample it at some intervals just before the drop falls. Now between the sampling periods, the recorder is maintained and then it is measured. The major advantage of this sampling is that it reduces large current fluctuations due to continuous growth and fall of the drops. Here we can see in figure 7.4, it shows a sampled DC polarigram. Here the this is the simplest representation of the voltammogram for a sample DC polarigram. So this is the LSV in which the solution or the electrode is kept in motion. It is called as hydrodynamic voltammetry. Now coming to the details of hydrodynamic voltammetry. So here in this process, the current is measured as a function of the potential applied to a solid working electrode that is kept in a stirring solution. The linear scan profiles are used while the solution is in motion towards the electrode. The cell has three electrodes: the working electrode, that is usually the mercury coated electrode, the reference electrode, that is the standard calomel electrode, and the counter electrode, that is usually the platinum coil. So the current in the cell, it passes between the working electrode and counter electrode. The electroactive substance that undergoes electroreactions at the microelectrode is brought to the electrode by three modes. So first is the migration of the charged ions under the influence of an electric field, the convection resulting from stirring or vibration, and the diffusion due to the coefficient gradient of the electrodes. So here this is the current that is proportional to the concentration of electroactive substance, and here it is given by the equation in 7.2. So here figure 7.5, it shows a three electrode cell for hydrodynamic voltammetry. So here the stirring is first done using a magnetic stirrer, but in other cases a stirrer has been provided. The voltammogram is a way when the current voltage plot is characterized by the EHAB value. So at this potential, the ions, they reach the discharge immediately, and thus the concentration of the analyte in the diffusion layer is almost nil. So another way of carrying out this hydrodynamic voltammetry, it involves the flowing of the analyte solution through the tube in which the micro electrode, here it is, this is the micro electrode, this is the solution, and here it is fixed. Now this technique, it has been used as a voltammetric detector in HPLC, that is high performance liquid chromatography. So some of the important applications of this hydrodynamic voltammetry is in the detection and determination of oxygen and chemical species like glucose, lactose, and sucrose. This detector has also been used in fundamental studies in electrochemistry and detection of endpoints in electrometric and volumetric titrations. Now coming to the different types of pulse methods in voltammetry. So now we know that the LSV or the linear sweep voltammetry, it is limited by charging current which is initially in the drop life. So however, the slowness inconvenient, they were the reasons for its decline. So in order to improve this, there are four important pulse methods that were developed. One is normal pulse voltammetry or polarography. The second is the differential pulsed voltammetry or polarography, square wave voltammetry, or cyclic voltammetry. So now we will talk about normal pulse polarography. So in this technique, the potential is altered by using square wave potential pulses and is applied only for about 50 ms before each current measurement. So the data have the same shapes as the linear sweep voltammetry, but the sensitivity is increased here. The dropping mercury electrode, it is held at a initial position. However, very little electrolysis and depletion occurs. So during the last 15 ms before the expiration of the pulse time, the current is measured. So this is more advanced in than the normal LSV. Then coming to differential pulse polarography, or we call it as DPP. So this is one improved from form of voltammogram. Here in figure 7.6, some of the basic parameters has been shown. So here when we look at DPP, this is how the plot looks like. So here in DPP, a 50 MB pulse is applied to the last 50 ms of the lifetime of the mercury drop. So the current here is measured twice during the lifetime of each drop, just before the pulse, and second one just before the drop falls. So the top of the peaks that is obtained here, it corresponds to the E half of the, here when we look the top of the peak, it corresponds to the E half value. The peak current in differential pulsed voltammetry, it increases linearly with the concentration of the analyte. It also increases with the pulse amplitude, but in a complicated linear fashion. So in general practices, amplitudes greater than 100 MB, they are not used because we get a broader peak. Rather than getting a sharp peak, a broad peak is obtained. So here figure 7.7, it shows the pulsed application procedure and current potential curves for normal pulse voltammetry and differential pulse voltammetry. These are the two different curves that can be obtained by the pulsed applications of voltammetry. So the higher detection limit in this process is due to superior discrimination against the charging current and impurity Faraday current. The peak current in the DPP, that is the differential pulsed polarography, is given by equation 7.3. Here IP represents the peak current, small n represents the number of the exchanged electrons, F is the Faraday constant, R is the gas constant, T is the temperature in Kelvin scale, capital A is the surface area of the electrode, Ca is the concentration of the analyte, EA, delta EA is the difference in the amplitude of the pulse, capital D is the diffusion coefficient, and TP is the pulse duration. So the detection limit for the determination by this technique, it is similar to square wave polarography at 10 to the power minus 7 to 10 to the power minus 8 moles per liter. But for irreversible reaction, this value is lowered. Now coming to square wave polarography or voltammetry. So this type of pulsed polarography offers the advantage of high sensitivity, great speed and low detection limit. So the entire voltammogram is obtained in less than 10 millisecond. So it uses a potential waveform similar to one that is used in differential pulsed polarography, and the entire potential sequence is applied during the lifetime of a single drop. This can be used with a DME or a hanging mercury drop electrode. The excitation signal in this technique is obtained by superimposing with uh, the pulse that is shown in the staircase signal. However, for reversible reactions, a large pulse is required. So the forward pulse, it gives us the cathodic current, that is I1, whereas the reverse pulse, it gives us the anodic current, that is I2, and the difference, that is delta I, is equal to I2 minus I1. It is plotted to give the voltammograms. This difference is directly proportional to the concentration. The potential at the peak corresponds to that of E half. So now it is possible to increase the precision of the analysis by signal averaging data from several voltammetric scans. The detection limit, they are reported to be of the order of 10 to the power minus 7 to 10 to the power minus 8 molar. So the peak current in this technique is given by the formula. Here it is shown in equation 7.4. The IP represents the peak current, K is a constant, N is the number of electrons involved in the reaction, D is the diffusion constant, delta E represents the difference in pulse amplitude, and Ca is the concentration of the analyte. So using this formula, we can calculate the peak current that is involved in the voltammetry. Now coming to cyclic voltammetry. So cyclic voltammetry, as the name implies, it is a very important and it has been one of the most widely used methods for studying a number of concepts in electrochemistry, which is one of the most versatile electrochemical species. Now, why CV is most effective? It is because of its capability for observing the change in the redox behavior of a material over a wide range of potential. So the resulting voltammograph, it is similar to that of a conventional spectrum in that it conveys information as a function of energy scan. In spite of its very wide applications, the mechanism of this of the technique is not generally well understood. However, this still till today this CV, it finds a great use in many analytical chemistry reactions. Then coming to fundamentals of cyclic voltammetry. So here in figure 7.8, you can see a typical cyclic voltammogram. So coming to fundamentals of cyclic voltammetry. So it consists of cycling the potential of a electrode that is immersed in an unstirred solution of the electroactive species and then measuring the resulting current. The potential of the working electrode is controlled versus a reference electrode such as a SCE or a silver chloride electrode. The controlling potential which is applied across these two electrodes can be considered as an excitation signal. The excitation signal for CV is a linear potential and it occurs in a triangular waveform like the one that is shown in figure 7.9. So this triangular potential wave signal, it sweeps the potential of the electrode between two values, that is between this peak value and this peak value, and it is called as the switching potentials. The excitation potentials here in figure 7.9, it causes the first potential to scan negatively from the initial potential to the final potential versus the SCE. So which results in the formation of a positive sign back to its original potential. Now the scan rate as reflected by the slope is 50 millivolt per second and the second cycle is indicated by the dark line. So multiple like cycles can also be used here. In figure 7.10, here is a cyclic voltammogram of potassium ferrocyanide. So a cyclic voltammogram, it is obtained by measuring the current at the working electrode during the potential scan. The current can be considered the response signal to the potential excitation signal. The voltammogram is a display of current, that is versus if current is taken in the vertical axis versus the potential which is taken in the x-axis. Since the potential, it varies linearly with time, the horizontal axis can be thought of a time axis. So this will be helpful in understanding the basic principle of the technique. So typical voltammogram, here it is shown in figure 7.10. So in a platinum working electrode is a solution containing 6 millimolar of potassium ferrocyanide as the electroactive species in 1 molar KNO3 in water as the supporting electrolyte. The potential excitation signal used to obtain this voltammogram, here it is shown in figure 7.9, but with a negative switching potential of minus 0.15 volt. Thus the vertical axis in figure 7.9, here it is now the horizontal axis. So when the potential is very sufficiently close to reduce the ferrocyanide ion, then the cathodic current here is due to the electrode process. Here what happens is the cathodic current increases rapidly until the concentration of the 3 minus, that is the ferrocyanide ion, here is substantially reduced. the current then for it decays, and after the electrode is depleted of the ferrocyanide ion due to the conversion of the ferricyanide ion, then the scan direction is reversed, and this is how we can analyze the cyclic voltammogram of ferrocyanide ion. So here the potential, if we look into the uh, potential excitation using the Nernst equation, we can find that it is given as E is equal to E0 plus 0.0591 by 1. Here in the denominator, 1 is used because one electron is involved in the process, and the log of the concentration of the reactant species. So the two important parameters of a cyclic voltammogram, they are the magnitudes of the anodic current IPA and the cathodic current IPE, and the anodic peak potential, that is EPA, and cathodic peak potential EPC. So these parameters, they have been labeled in figure 7.10. One method of measuring the IP, that is the here is the peak current. It involves the extrapolation of a baseline current that has been shown in figure 7.10. So it is generally difficult for complicated systems. However, the peak current for reversible system was described by Randall's Sevick equation here for the forward step of the sweep of the first cycle, and here it is given as IP is equal to 2.686 into 10 to the power 5 into n to the power 3 by 2 into AD to the power half into C0 nu to the power half. So here in equation 7.8, the IP represents the peak current, N is the number of electrons, A is the electrode area, D is the diffusion coefficient, C0 is the concentration of the analyte, and nu is the scan rate. So now from equation 7.8, we can see that IP is directly proportional to the concentration if other parameters are kept constant. So this relationship to concentration or and the peak current, they are very important. So we know that the value of IPA, that is the anodic peak current, and IPC, that is the cathodic peak current, it should be identical for a simple couple, so that we have IPA by IPC is equal to 1. So now also from equation 7.8, we see that the IP, that is the peak current, is also directly proportional to the nu to the power half, where nu is the scan rate. However, the ratio of peak currents, they can be significantly affected by different types of chemical reactions that occur within the electrodes. So a redox couple in which both species, they rapidly exchange electrons with the working electrode is called as an electrochemically reversible couple. Then the formal reduction potential for the reversible couple can be given as E0 is equal to EPA plus EPC by 2. The number of electrons transferred in the electrode reaction, that is N, it can be determined from the separation between the peak potentials, and here delta EP is given as 0.059 by N. Thus for a one electron process, such as for the reduction of ferrocyanide to ferricyanide, EP has been found to be 0.059 volt. Slower electron transfer at the electron surface, it causes the peak separation delta E to increase. So the electrochemical irreversibility is caused by slow electron exchange of the redox species with the working electrode. So in this case, when we look into equations 7.8, 9 and 11, 10 and 11, they are not applicable. So the electrochemical irreversibility is mostly characterized by a separation of peak potential that is indicated by this equation. So here the electrochemical irreversibility is caused by slow electron exchange of the redox species with the working electrode. The process is said to be quasi-reversible if it is reversible at low sweep rates but becomes irreversible at higher ones after having pass through a region that is known as quasi-reversible at intermediate values. This transition from reversibility occurs when the relative rate of electron transfer with respect to that of mass transfer is insufficient to maintain the nernst equilibrium. So peak separation is greater than the predicted theoretical value. It is typically caused by the IR drop, that is the ohmic resistance, due to high resistance between working and reference electrode. This is especially a problem as fast scan rates where I can be large and in non-aqueous solvents where R can be large. So the various criteria applied for the diagnosis of reversibility, irreversibility or quasi-reversibility, they have been summarized here in table 7.1. So here in table 7.1, the criteria for a reversible system is E is equal to EPA minus EPC. EPA is equal to 0.0591 to the power by N is equal to B. The EP is independent of nu, and the criteria for quasi-reversible system is IP increases with nu hub but not proportional to it. EPA is greater than 0.059 by N and it increases with nu. EPC shifts negatively with increasing nu. Then coming to the criteria for total irreversible system is no reverse peak. IP is directly proportional to nu to the power half. EPC is directly proportional to minus 30 by alpha into n alpha star, and EP minus E half is equal to alpha 48 by alpha C n alpha. So here the most marked feature for a cyclic voltammogram of a total irreversible system is the total absence of a reverse peak. However, such an instrument on its own does not necessarily imply an irreversible electron transfer process but could be due to the fast chemical reactions. Now coming to the instrumentation of CV. Here in figure 7.11, a simple diagrammatic representation of the cyclic voltammetry instrumentation has been shown. So first, CV requires a waveform generator to produce the excitation signal, and it requires a potentiostat to apply this signal to an electrochemical cell similar to a polarographic cell, a current to voltage converter to measure the resulting current, and a XY recorder or a oscilloscope to display the voltammogram. So the first three items, they are normally integrated into a single electronic device. The potentiostat ensures that the working electrode potential will not be influenced by the reactions which takes place. The data that is obtained with XY recorder at a slow scan, that is less than 50 millivolt per second, while storage oscilloscope at faster rates having scan rate up to 20,000 volt per second, they have been used. So here in this figure, O represents the working electrode to reference electrode, and this is the here, and this it represents the auxiliary electrode. So modern potentiostat, they utilized a three electrode system here: a working electrode, a reference electrode, and an auxiliary electrode. So the potentiostat, it applies the desired potential between a working electrode and a reference electrode. The working electrode is the electrode on which the electrolysis of our interest it is kept. The current required to sustain the electrolysis is then provided by the auxiliary electrode. This arrangement, it prevents large amount of current from flowing to the reference electrode, and that could hamper its characteristics. A normal polarographic cell is usually used in this technique. These cells, they consist of a glass container which has holes for introducing either the electrodes or the passage of nitrogen gas or an inert gas for the removal of oxygen from the system. The reference electrode is a SCE, that is the standard calomel electrode, or AgAgCl electrode, which is often isolated from the solution with a salt bridge to prevent contamination by leakage from the reference electrode. The auxiliary electrode is usually a platinum wire that is placed directly into the solution. Since the limiting current in is temperature dependent, then the cell is thermostated. So cells are commercially, they are available, and they require around 1 to 2 ml of the solution. So even thin cells are used where 60 microliters of the solution have been used. Now, a large variety of working electrodes, they have been used in voltammetry. The dropping mercury electrode is used specially in polarography, and the hanging mercury drop electrode is used in cyclic voltammetry. So here a very thin coat of mercury, it is deposited on the substrate such as the graphite to form a mercury film electrode. So a significant advantage of the mercury is because of its negative potential range. So solid electrodes that are made up of platinum, gold, glassy carbon, they are also used in cyclic voltammetry. Such electrodes, they have a better positive potential range than the mercury. So, in conclusion, we can say that CV has become increasingly popular in all fields of chemistry as a means of studying redox reactions. This technique, it enables a wide potential range to be scanned rapidly for reducible or oxidizable substances. This capability, together with its variable time scale and good sensitivity, makes it a very versatile electrochemical technique. At the same time, it must be emphasized that its merits are mostly in the realm of qualitative or diagnostic purposes. Quantitative measurements, they are best obtained by the pulsed technique. Due to the kinetic control of many CV measurements, caution is always advisable, and while evaluating the the thermodynamic parameters mostly. So now coming to stripping methods. So here in stripping methods, it is a very sensitive electrochemical technique for the quantitative analysis of micro quantitative electroactive analytes which oxidize or reduce reversibly at solid electrodes or form or form insoluble species at the electrode surface. Basically, two types of steps are involved in this process. The first is the analyte of interest is electrolytically deposited on the working electrode by controlled potential electrolysis, and the second is a reverse potential seal or stripping seal is applied, in which the deposited analyte is removed from the electrolyte. So here among among the two steps, the first step is basically pre-concentration or electrodeposition, while the second one is the stripping step. So three different types of stripping techniques are possible. One is anodic stripping voltammetry. So here this process is used to determine trace amount of metal ions that can be pre-concentrated at an electrode by reduction to its metallic state. The microelectrode, it behaves as a cathode during the deposition step and as an anode during the stripping step, and the analyte being oxidized to its original form. So this may be explained in detail, like for taking the example of copper 2 plus, the deposition reaction at the mercury drop electrode can be given by equation 7.12. Now where CuHg here is amalgamation with mercury. This step is basically a pre-concentration step where the metal ion is concentrated on a small volume over the electrode. The solution is stirred during electrolysis to increase the rate of deposition. Near the end of deposition time, the stirring is stopped, and usually after 1 to 30 minutes, mostly 30 minutes, they are used for deposition. So in the second step, the potential is scanned anodically towards more positive potential. When the potential becomes positive, the analyte is stripped from the electrode, returning to its oxidized form. So here it is in the second step, and the current during this step is monitored as a function of potential, giving rise to the voltammogram. This technique is sensitive to environmental conditions like the area of the electrode or the size of the mercury drop. Now, if properly the conditions are controlled, then this method is sensitive and accurate results can be obtained. So here in figure 7.12, details of stripping voltammetry has been shown. In anodic stripping voltammetry, the determination of the analyte, it is based on the anodic dissolution. This process is followed voltammetrically and the peak current thus obtained, it is proportional to the potential scan rate and the radius of the mercury drop. So in both the cases, the peak current is given by the two equations that is represented in equation 7.14. So where the IP is the peak current, N is the number of electrons during the transfer process, D is the diffusion constant, K is the constant, Cm is the concentration of the metal in the amalgam, A is the surface area, and U is the scan rate, where TACE represents the accumulation time. However, in both the cases, we see that the peak current depends on the accumulation time and also is proportional to the concentration of the amalgam of the metal ion and in the amalgam, and it is indirectly proportional to the concentration of analyte in the sample solution. So the peak currents in this technique, they are a linear function of concentration, and hence this technique, it can be used for the determination of ions in even they are present in trace quantities. Now coming to cathodic stripping voltammetry. So it is used for the determination of ions that form insoluble mercury salts at the mercury surface or insoluble silver salts on a silver electrode. The experimental design is similar to that for ASV, that is anodic stripping voltammetry. However, two modifications are made. The decomposition step, it involves the oxidation of the mercury electrode to Hg2+, which then reacts with the analyte to form a insoluble film at the surface. So the decomposition step with HCl can be given as Hg plus 2Cl forming HgCl2, and the stripping step, that is the second step, is followed by scanning cathodically towards a more negative potential. So here, and it is here, it is shown in figure equation 7.16. So some of the analytes that can be analyzed using CSV, that is cathodic stripping voltammetry, are halides, sulfides, mercaptans, etc. Then coming to adsorptive stripping voltammetry. So in this technique, the analyte is adsorbed on the electrode surface and there is no electrolysis step, and after complete deposition, the potential is scanned in anodic or cathodic direction depending whether our analyte is oxidized or reduced. The deposition step in this method amounts to an electrochemical pre-concentration of the analyte, that is the concentration of the analyte on the surface of the microelectrode is greater than the bulk of solution, and hence these methods, they are extremely sensitive and the detection limit can be improved by factors of 10 to the power 6. So some analytes that can be tested using this method is cocaine. Then coming to the alternating current methods. So here in this technique, the linear potential is modulated by a sine wave potential, the sine wave voltage of a small amplitude. So this produces an AC whose size is determined by the direct potential applied and which is greatest at the half wave potential. So the plot of the selectively measured AC against the potential, it gives a peak shaped alternative current polarigram here as it is shown in figure 7.13. So a simplified expression for the peak current can be given as IP is equal to K into N square into E into F into CA. So IP is the peak current, K is the constant, E represents the amplitude of the superimposed AC, Ca is the concentration, N is the number of electrons that are involved in the reaction, and F is the frequency. Thus, the height of the AC polarographic peak, it can be used to determine the concentration in a way similar to DC polarographic method. The AC polarographic peak currents, they are widely dependent on the kinetics of charge transfer reactions and the signals of strongly irreversible processes are suppressed. Now, for reversible reactions, the half width of the peak, that is B half, is equal to 90 by n. It depends on the electron exchange, as a result of which large values of n and B will be narrower, and the with slow process B will be broader. So AC polarographic determinations, they are limited to a sensitivity of about 10 to the power minus 5 moles per liter because of high capacitance current contribution, which is the main source for periodic charging and discharging of the double layer. The above sensitivity for reversible redox processes, they can be improved to about 5 to 10 to the power minus 7 moles per liter if the AC is measured at a particular phase drift with reference to the excitation signal. So this is the first harmonic AC polarography, or we call it as AC1 polarography. The measurement of the harmonic with the aid of phase selective rectification, that is AC2, it reduces the capacitance current contribution, thus increasing the sensitivity of the selectivity of the determination. So then coming to the voltammetry, or that is the instrument. So the basic instrument, it consists of two components. Now here in figure 7.14, the basic instrumentation can be shown. So first is a normal 3 electrode graph. Second is linear scan voltage generator to give different types of signals. The polarographic cell is made of with 3 electrodes. It is dipped in a solution containing the electroactive species, that is usually called as the supporting electrolyte. Third is the working electrode. It is a microelectrode whose potential varies linearly with time. The reference electrode, that is normally a standard electrode, is used whose potential is constant throughout the experiment. That is mostly saturated calomel electrode, that is SCE, or silver chloride electrode. Then there is also a counter electrode. It is a platinum coil or a mercury pool that simply serves to conduct electricity from the signal source through the solution to the microelectrode. The potentiostat, it allows to impose the potential scanning between the working and reference electrode, while the current flowing through the circuit is recorded between the working and the auxiliary electrodes. So the computer trace analyzer has been used as can be used as an integrated system with a computer or a keyboard to measure, and different softwares are available. The softwares, they send the scanning parameters to the potentiostatic analyzer to check its correctness and accuracy, and the softwares also handle the current potential output data. So in summary, we have talked about different types of voltammetry. Then we have talked about the DC and AC, the DC polarography, and we have also talked about the stripping polarimetry and voltammetry, and the alternating current methods have also been discussed. So we'll just take a break of 5 minutes, then again resume with the next chapter. So now we'll start with the other unit, that is polarographic and amperometric titrations. So here we will be talking about the different types of polarography and different types of amperometric titrations. So first is, we'll begin with what is polarography. So polarography is the earliest voltammetric technique. It was developed by Herovsky, and he was awarded the Nobel Prize for developing this polarographic technique. So now, according to Ilkovic equation, we know that the diffusion current is directly proportional to the concentration. That is, ID is directly proportional to C, or ID is equal to Kc. So if some of the electroactive material in the solution, it is removed by interaction with some other reagents, then the diffusion coefficient or the current, it will decrease. Now this is the fundamental principle of amperometric titrations, or we call them polarographic titrations. So most metals, they are reducible at the dropping mercury electrode, and multi-component mixture can often be analyzed if we select appropriate supporting electrolyte, so that their half-wave potential of the two ions, they are just differed by about -2 volt versus SCE, or by using complex agents by taking advantage of this process. Now, based on this, polarography is predominantly used for trace metal analysis, also for ultra pure metals, minerals, metallurgy, food stuffs, beverages, and clinical analysis. The reducible anions such as bromate, iodate, chromate, dichromate, and nitrite can also be determined using well buffered solutions. Now, during the electrolysis, the chemical reactions, it occur under the influence of an electromotive force at electrodes immersed in the solution. The reactions occurring at the electrodes, that is the electrode reactions, they are characterized by the transfer of electrons between the electrode and the substances in solution. Because of this, the equality of positive and negative ions, they are unbalanced at the electrode, but is counteracted by oppositely directed movement of positive and negative ions through the solution to produce the flow of the current. Figure 8.1, we see a typical polarogram. Here, the x-axis is the applied potential in volts, and the y-axis is the current in microamperes. So this is the current which is actually measured by the movement of electrons in the external circuit connecting the two electrodes. Therefore, the current is the result of the electrode reaction. The electrode at which reduction occurs is the cathode, and the electrode at which oxidation occurs is the anode. The curve obtained by plotting EMF applied to a cell against the resulting current is called as the current voltage curve. Now, when the applied potential is equal to the decomposition potential of the electroactive substance, then the current, cathode current, it starts increasing due to this following cathodic reaction. So, the resulting zinc amalgam, it forms at the surface of the electrode. So as a result of the potential of the dropping mercury electrode is becomes more negative, there is further increase in current in according to Ohm's law, and the concentration of zinc plus is reduced until it reaches a point whereas it becomes extremely small. So here the number of zinc ions that diffuses from the bulk of the solution to the electrode is equal to the number that is deposited during the rate of the diffusion. That is, we can say the rate of the diffusion is equal to the rate of the reduction. Now, when the applied DMF, it exceeds the decomposition potential, then the DME becomes depolarized, as Zn2 plus will become Zn0, forming amalgam, and there is a reversible electrode reaction. So, as long as the electrode is ideally depolarized, the passage of current, it does not cause the potential to deviate from its reversible value, and it is determined from the Nernst equation that is given in equation 8.1. So, here because of this, we can say that the so-called the plot obtained is called as a polarogram. Then the dropping mercury electrode, or the DME. So this small polarizable electrode is produced by passing a stream of mercury through a resistance glass capillary having a very fine bore of 0.05 to 0.08 mm internal diameter and 5 to 9 cm long. The drop, it falls at a steady rate of 3 to 5 seconds per drop and is adjusted under a head of 40 to 60 centimeter of mercury. The current oscillates between a near zero value as drop falls from the capillary to a maximum value, and it has the following several advantages. That is, its surface area is reproducible with a given capillary. The constant renewal of the electrode surface eliminates passivity or poisoning effects. The large hydrogen over potential on the mercury, it renders possible the deposition of substances difficult to reduce, such as aluminium ion and manganese ion, The mercury forms an amalgam with many metals. The diffusion current, it assumes a steady value immediately and it is reproducible in nature. And the surface area of the electrode can be calculated from the weight of the drops. The dropping mercury electrode therefore is useful over the range of plus zero point 0.3 to minus 2.2 volt versus the SCE. So above plus plus 0.4 volt, the mercury dissolves and it gives an anodic wave due to the oxidation of the mercury 1 ion to mercury 2 plus. At the potentials that is more negative, that is greater than minus 1.8 volt, visible hydrogen evolution it occurs in the acidic solution, and at minus 2 volt the supporting electrolytes they begin to discharge. So here in figure 8.2 there is a current oscillation with DME. Here it is the general, the average response of a CV curve. Then coming to migration and limiting currents. So the limiting current obtained with the dropping mercury electrode is caused by the extreme state of concentration polarization, which results from the depletion of the concentration of the electroreducible or electro-oxidizable substances. The reduced or oxidized substances, they are supplied to the depleted region by two forces. One is the diffusive force, which is proportional to the concentration gradient, and the other is the electrical force, which is proportional to the electric potential. So here, so the limiting current is often regarded as the sum of the diffusion current and that of the migration current. So now coming to migration current. The migration current is due to the migration of the reduced or oxidized ions, which is proportional to the electric potential gradient at the electrode due to attraction. So under this potential gradient, unless it is removed, then the limiting current it cannot be proportional to the concentration of the electroactive ions in solution. So commonly used supporting electrolytes are mostly potassium or sodium salts. The potassium ions they cannot be discharged at cathode until the voltage is applied is very large. The large number of potassium ions therefore they remain as a crowd around cathode and restrict the potential gradient to a region very close to the electrode surface. So there is no longer an electrostatic attraction that is operative to one another. So at this situation, the limiting current is solely governed by the diffusion of the species. So the migration current it depends on the transference number of the reducible or oxidizable ion in the solution and the total limiting current, and it is given as Im is equal to Ti into Ii. So here in table 8.1 the limiting current in solutions containing various concentrations of supporting electrolytes has been shown. So here is the KNO3 concentration, the transference number and the limiting current in microamperes has been shown. So here from table 1 8.1 we see that the transference number of an ion it decreased practically to zero in the presence of 100-fold excess of a supporting electrolyte. Like if we have 1 molar, then it decreased, the transference number becomes almost closer to zero. Now, in such solutions, almost all the current is carried through the cell by the potassium and nitrate ions. However, these are not reduced before the evolution of hydrogen, and so the reduction of lead ions remains the only process by which the electrons can be transferred. So now coming to diffusion and residual currents. So in the first is the diffusion current. Now when we have an excess supporting electrolyte, then the electrical force on the reduced or the oxidizing species that becomes zero. So thus the limiting current it becomes the sole factor for the diffusion current. So here Ilkovic he examined the various factors and a theoretical formula was given where ID, that is the diffusion current, is equal to 607 into NCD to the power half into M into 2 by 3 into T to the power 1 by 6, where ID is the diffusion current, N is the number of electrons involved in the whole process, D is the diffusion coefficient, C is the concentration of our electroactive species, M is the rate of flow of mercury, and T is the drop time of mercury in seconds. So, using the theoretical equation, we can find the diffusion current through a electroactive species. Now, we have in equation 8.3, there is a constant that is given as 607. So this is a combination of different natural constants and the including the Faraday. So now this equation is very important, because from this equation, if we keep all other factors constant, we see that ID is directly proportional to C. So that is the concentration. So thus we see that the diffusion current is directly proportional to the concentration of the electroactive species. Thus this theorem is very important in quantitative polarographic analysis. Then coming to residual current. So even there is when there is an absence of electroactive species, then the solution that has only supporting electrolytes, that allows a small current which pass through it, and these are called as residual currents. So a residual currents is usually, it contains two parts. So the first is the reduction of trace impurities or the Faraday current present in the large concentration of the supporting electrolyte. So these include the dissolved oxygen, the traces of metal ions such as ferric iron, lead, and arsenic. So out of these, dissolved oxygen, it can be removed by passing pure nitrogen for 10 to 15 minutes before taking a CV curve. The second component of a residual current is charging current or capacitive current, which is non-Faradic, and it is present whenever the working electrode potential changes. The mercury here, it is covered with an electrical double layer of positively and negatively charged ions of the electrolyte. The capacity of the double layer and hence the charging of the current, it varies depending on the potential that is applied. So here in figure 8.3, it shows a residual current for a zero point 0.1 molar solution of HCl. This residual current is responsible for determining the accuracy and sensitivity of a polarographic method at low concentrations of electroactive substances below 10 to the power minus 4 molar. At concentrations around 10 to the power minus 5 molar of electroactive species, the residual current is larger than the Faraday current, and it is therefore not very sensitive. Then the factors that affecting the diffusion current. So the Ilkovic equation is very important because it shows the linear relationship between ID and C. It also accounts for other factors which influence the diffusion current, and these factors are the concentration, the dimensions of the capillary, and the pressure on the dropping mercury, the temperature, the viscosity of the medium, and other factors. So first we will talk about the concentration of the electroactive substance. Now we know that according to Ilkovic equation, ID is directly proportional to C. So this forms the basis of quantitative polarographic analysis. But there are certain cases where ID versus C is not constant and the current is determined by the applying the chemical kinetics. So that is a very rare case. Then coming to the capillary characteristics and the factors that influence them. So from Ilkovic equation, we see that diffusion current also depends on M and T, which are together or collectively they are called as capillary characteristics and are therefore affected by their variations. M is directly proportional and T is inversely proportional to the pressure of the mercury drop. Now these effects, they have been reported in terms of mercury column above the capillary tip. So accordingly, M2 by 3, T1 by 6 is proportional to delta H correction factor and the current diffusion current in the Ilkovic equation. So here we see that ID by delta H is equal to K dash. So any deviation from this equation, it indicates that the current must be partly or wholly governed by the rate of some process other than the diffusion of electroactive substances. Now here in table 8.2, the effect of pressure on M and T has been shown here. including the H correction, it includes the correction in centimeter. Then coming to the influence of temperature. So the change in temperature, it affects all the values in the Ilkovic equation except the value of N, that is the number of electroactive species involved in the reaction. The temperature coefficient of M is about plus 0.27 percentage per degree, while that of T is about minus 0.22% per degree. So the temperature coefficient is about plus 1.5 0.15% per degree. So this temperature coefficient is also, and the is also closer to the diffusion coefficient, and the numerical constant that is present in Ilkovic equation, that is 60Z is 7, is also influenced by this temperature coefficient. So combining all the values, it has been shown that the temperature coefficient of diffusion current as plus 0.13 per degree. So the diffusion current increases 1.3% per 1 degree rise in temperature. Hence, it is always advised to keep the temperature range within a constant of plus minus zero point 0.5 degree. Then coming to the influence of solvent and the supporting electrolyte on the Ilkovic equation. Now we know that the diffusion current depends on the viscosity of the medium. We know that ID decreases with increase in viscosity because D is inversely proportional to viscosity of the medium. So therefore, as per the equation, ID is directly proportional to eta to the power half. Eta, that is the viscosity, it varies as the aqueous solution. They changed partly to non-aqueous medium using solvents such as methanol dioxide. So it is very important to keep the concentration of every constituent of the supporting electrolyte within plus minus 10% to ensure that the variation in the diffusion current resulting from the viscosity effect is very nil or is negligible. Now coming to polarographic equation. So let us first consider a general electrode reaction. Here is oxidation, gaining of n number of electrons, it becomes reduced. So the electrode potential for such type of reversible reaction can be given in equation 8.5, where A represents the activities of the oxidant and reductant. Now substituting all the constant, this equation 8.5, it becomes 8.6. So before the commencement of the polarographic wave, only a small residual current flows and the concentration of the electroactive material, it remains the same in all direction. So as soon as the EMF, the applied EMF, it exceeds the decomposition potential of the material, some of the reversible substance at the electrode solution interface is reduced and its concentration begin to decrease. Since there is a gradient, concentration gradient, so the bulk of the solution, so the ions from the bulk of the solution, they will move to the interface by means of diffusion. So this current or the movement is given the is caused by a current which is given as I is equal to K1 into oxidation at the 0 and the oxidation at occurring at time t. So here it is according to here. So if we put this value in Ilkovic equation, we get K1 to be this value. So now when the current attains the limiting value represented by the diffusion current plateau, so it becomes 0. The currents therefore is ID, and here it becomes I is equal to K1 into the concentration of the oxidant, which becomes equal to ID. So combining equation 8.7 and 8.8, we obtain equation 9. Similarly, in terms of a reductant, we can obtain the here from equation 10 can be obtained in terms of the concentration of the reductant. Now, if the reductant is soluble in water, it will diffuse from the surface of the electrode to the bulk of the solution. So, the concentration of the reductant at the surface at any time I will be proportional to the rate of diffusion from of the reductant. So, substituting all this value, we get E value is equal to E0 minus this. Then we have halfway potential. We know E half, that is halfway potential, is given as I is equal to ID by 2. So then substituting the value, we can write equation 8.11 as equation 8.13, that is E is equal to E half minus 0.059 by n into log of I by ID minus I. Now this equation, it is called as the equation of the polarographic wave, and it represents the potential as a function of current at any time period of the polarographic wave. So this is a very important equation for polarography. Now coming to the E half and its effect on complexing agents. So first we'll talk about the half-wave potential. So the electroactive material in polarography is characterized by its half-wave potential E half. So under any set of experimental conditions, each substance has its own characteristic E half, and this forms the fundamentals of polarographic analysis. So the half-wave potential, it is defined as the potential at which the current due to the reduction or oxidation is responsible is seen as a half as large on the plateau. So here, like figure 8.4a and 8.4b. So in 8.4a, so we were discussing the effect of complexing agents. So here we see the when a complexation of metal, it proceeds in two steps, and that is represented in equation 8.14 and 8.15. So the E half of the metal ion, it is shifted to the more negative value. So and the expression for the potential of such a system, it can be given as E half is equal to E0 plus 0.0591 by n log of k minus 0.0591 by n into log of x to the power b minus. So here x to the power b minus indicates the complexing agent. The p is determined by taking E half values with different concentrations of the complexing agent. So now if we plot a graph between the log of concentration of x and E half, then that is shown in figure 8.5a 8.5, we see a line with a slope equivalent to this value. So and from the slope we can determine the p. So once we know the value of p, that is p is called as the instability constant of the complex, then the shift of the E half of metal by complexation, it can be done. And once we know the value of p, the following the E half can be calculated. That here table 8.3, it shows the E half value of metal ions in complexing and non-complexing mediums at DME. Then coming to determination of n and reversibility. Now from equation 8.13 we see that a plot of I by id minus I, here log of I by I, it is plotted against the potential, then a straight line is obtained. The slope of this line is equal to 0.0591 by n. If the n is an integer, we can say that the electrode reaction for this wave is reversible. Now, if the slope of this log plot, it is larger than n, then we see it is an irreversible reaction. Then the halfway potential here, the halfway potential here, that we from this figure, for a reversible wave it can be easily known, the halfway potential, it can be easily found out from a log plot, that is here in figure 8.6, it is the log id minus I by I versus the p. So this is also one way to calculate the applied potential. Another method to determine the reversibility of a electrode reaction, which is very simple, is by measuring the potential corresponding to 1/3 or 3/4 of the polarigram. So at 1 by 4 for a reversible cathodic wave, E 1 by 4 is equal to E half minus 0.0591 by n log of id by 4, id minus id by 4, and similarly E 3 by 4 can be given from this value. Therefore the value of E3 by 4 minus E1 by 4 becomes equal to minus 56.4 by n. So, and for a reversible anodic wave, it is equal to plus 56.4 by n millivolt. So, this is how it can be, the reversible nature can be known. Then we have irreversible reactions. Many electrode reactions, they are partially or totally irreversible in nature, like in the equation here it is shown. So here the polarigram in such cases is less defined, and the polarographic equation for such type of cases uses a new constant that is called as transfer coefficient, and it is used in the denominator that is shown in the equation 8.18. Now there are currents that are other than diffusion currents, such as kinetic currents, catalytic currents, absorption waves. So we'll study kinetic currents. Some substances, they are not electroactive, but they are made electroactive on chemical reactions. The products so formed by the chemical reactions, they undergo the reduction oxidation at the DME. So the waves of this kind, they are called as kinetic waves, and the mechanism responsible may be written as Y forward reaction O backward reaction Y. Y is not electroactive, but O is. So here Kf and Kb are the forward and backward reactions. Now for example of such type of reaction is, diol does not undergo reaction at DME, but on conversion to aldehyde, it is reducible, and the wave height reflects the rate of transformation of diol to aldehyde form. So here the kinetic current obtained is given by the equation in 8.20, and they are recognized from m2 by 3 into t2 by 3, which does not vary with the height. The kinetic currents, they are not much, practically they are not much in use. Also there is a possibility of impurities that might appear during the rate determination step. So we are mostly working with catalytic currents now. So when an electroactive species is reduced by the electrode by a normal process, here like O taking up electrons to form the reduced product R, then this R is in another solution. Here R reacts with Z to form O. Then because of the regeneration of this O, more and more O is reduced at the DME, and there is an increase in current that is called as the catalytic current. This process is continued until the applied potential is very much negative, corresponding to the limiting plateau of O. The average catalytic current over the life of a drop is given by this equation. So example, if the solution contains a small amount of hydrogen peroxide, it is regenerated by oxidation of this, then It is a few thousands of a microampere. Therefore, it is important for determining very low concentrations of original electroactive substances. The catalytic currents, they are identified as IC, is independent of correction factor, like those are used in kinetic currents. Then coming to adsorption waves, some electroactive species or their products, due to their electrooxidation or reduction, they get adsorbed on the mercury drop. So here, in such cases, if in the equation 8.24, if R is adsorbed, then the current obtained is small and a single wave is obtained whose height is proportional to O. So from the time the normal wave appears, the height of the adsorption wave remains constant. So the total wave of the first and second together is proportional to the constant of O, concentration of O, and diffusion is controlled. So here the adsorption waves, they are observed in solutions of thiols, certain inorganic mercurials, uracil, arsenic, etc. Here figure 8.8, it shows the polarigram of sodium propyl xanthate. And these adsorption waves, they have been used to evaluate the area of adsorbed species using the equation given below only when adsorption is seen without normal wave. Now coming to polarographic maxima, maximum suppressors. So current voltage curves, that is the IE curves, they are frequently distorted by increasing the current beyond the diffusing current, and rapidly they decrease to the normal diffusion plateau. This abnormal increase in current, it is referred to as maxima, and they vary in shape from sharp peaks to round bumps. So to measure the true dimension, the currents, the maximum must be eliminated. This can be done by adding small amount of surface active reagents. Those are gelatin, dyes, triton X100, which these substances, they form a layer on the mercury solution interface to prevent the movement on the diffusion layer inside the solution. So gelatin is widely used in the concentration of 0.002% to 0.01%. Higher concentration of gelatin has been known to suppress the diffusion currents also. So therefore, this concentration is mostly preferred. Others frequently used are triton X100 in the range of 0.002 to 0.004%, and methyl cellulose in the range of 0.05%. So here in figure 8.9, this is a polarigram of lead in potassium chloride. The A represents in absence of a suppressor, and B shows the addition of 0.002% sodium methyl red. Then coming to the qualitative and quantitative analysis of polarograms. So the qualitative analysis of sample, it is carried out by first matching its E half with the tabulated values that is available in the literature in the supporting electrolytes. It is also advisable to use the log plot to know the correct value of the E half. So here in table 8.4, the half-wave potentials of some common ions has been shown. Here the metal ion, the supporting electrolytes, and the E half values has been shown. For in table 8.4, a first part, it has been shown for 1 molar NH3 plus 1 molar NH4Cl. The second uses 2 molar acetic acid and 2 molar ammonium acetate with a suppressor, and the other table values has been shown. Then coming to quantitative polarographic analysis. So polarographic analysis, it can be used for to understand the for very to detection of very low concentration of substances ranging from 10 to the power minus 3 molar to 10 to the power minus 5 molar. So here, if we have solutions and if their half-wave potentials are known, then they can be determined. So if the half-wave potentials of two ions are very close, then such experimental devices can be employed, like precipitation of one, and like one element can be precipitated and other can be identified. Second is by complexation methods. So here in the there are three methods which have been used in practice. So on all these methods, the oxygen is removed first before taking the polarogram of the solution. So first is the wave height concentration plots, that is mostly called as the calibration plot. First, standard solutions of different concentration of ions under investigations, they are prepared using the same supporting electrolyte and 0.005% maximum suppressor, that is gelatin, and polarogram. So the wave heights of all known concentrations, they are noted down, and after making correction for residual current, a plot is drawn as a function concentration. Keeping the supporting electrolyte and gelatin as above, the polarogram of the unknown is recorded. So this is called as the calibration curve. Then coming to the internal standard method, the polarogram of unknown solution in a supporting electrolyte and gelatin is recorded, and to the same solution, a standard, or that is we call it as a pilot ion, is added in known quantity. The only condition is that the delta E half of the pilot ion, it should be unaffected and by Z plus 0.4 volt. Then coming to method of standard dilution. The polarogram of the unknown is first recorded, and then a known amount of standard solution of the same ion, it is added, and the second polarogram is taken. So then the comparison is made by using the following calculations. We know that ID1 is equal to K into Cu, and ID2 is equal to the K, that is the constant, the volume of the C, that U, that is the concentration of the unknown solution, plus the nu of the unknown solution divided by V plus nu. So this is for ID2. And we have therefore the concentration of the unknown solution, it can be known by using this equation. So such methods has been used for environmental analysis of different trace elements. Then coming to the instrumentation. So the basic instrumentation for a polarographic method, here it has been shown in figure 8.11. So it uses a polarographic cell and has an external reference electrode and is the H cell. It composed of two components, one which contains the solution to be studied and the other that contains the reference electrode. These components, they are separated by a cross member fluid that is filled with a saturated KCl gel, which is agar and saturated KCl. The second compartment is the solution into which the DME is inserted, and this is nitrogen inlet and outlet provision. This simple recording polarogram unit has a potentiometer P by which any EMF, it is gradually applied to the cell. So here in figure 8.1, this is a general representation of a polarographic analysis, and 8.12, it shows the photograph original of a polarographic unit. Then coming to amperometric titrations. So as per Ilkovic equation, we know that ID is directly proportional to C, or ID is equal to K into C. All other factors remaining constant. So if some of the electroactive material in the solution is removed by interaction with some other reagent, then the diffusion current will decrease proportionally. So here in figure 8.13, common types of curve with amperometric titrations have been shown here in figure 8.13A to D. So this is the fundamental principle of amperometric titration. The diffusion current at an appropriate applied voltage is measured as a function of the volume of the titrating solution. So the endpoint is observed by the intersection of two lines, and which gives us the after the equivalence point. Here, this is how the endpoint is observed. The voltage applied at the beginning of the titration must be selected so that the diffusion current of the substance to be titrated or of the reagent is obtained. So depending on the selection of the applied potential, then the titration proceeds and different types of titration curves are obtained. So for each titration, the applied voltage is selected to the value between x and y, here as between the values of x and y, that is shown, and the shown in figures in A-2 here. This is how they are plotted, and x and y values have been found out. Then in the electro in figure 8.3a, we see that the electroactive material is being removed from the solution by precipitation or complex formation with an inactive titrant. So here in figure 8.3a, we see how the volume of the reagent varies with the current when an electroactive material is removed from the solution by precipitation. In this way, different other the plots have been discussed. The titration cell, it is basically made of a Pyrex glass, three-necked, and it is a flat bottom into which a microburette, a dropping mercury, that is the electrode, and a gas outlet for nitrogen has been provided. So the cell here, it is connected to a reference electrode in the form of an attachment with a sintered disc separating the titration cell and the reference electrode. So the general procedure is that we take a known volume of the solution inside the titration cell, and the supporting electrolyte is added and the cell is connected to the terminals. So when first oxygen is passed out by dissolving nitrogen into the container, the known volume of the reagent is added from the microburette, and then again nitrogen is passed for 2 minutes and then stopped. The current and burette readings are noted. Now then this procedure is repeated, and then from the plot we obtain the endpoint. Then coming to the advantages of amperometry. The titration can usually be carried out very rapidly since the endpoint is found graphically. Second is the titrations can be carried out in cases in which the solubility relations are such that the potentiometric or visual indicator methods are much unsatisfactory. A number of amperometric titrations, they can be carried out at dilutions of in the range of 10 to the power minus 4 molar, at which many visual or other titrations can no longer be possible. The foreign salts which may be present, they interfere, and they are added as supporting electrolyte in order to eliminate the migration of current, which is not possible in conductometric titration. The results of the titration are independent of the characteristics of the capillary. The temperature need not be known provided it is kept during constant during the titration. Although a polarograph is convenient as a means of applying the voltage to the cell, its use is not essential in amperometric titration. The constant applied voltage may be obtained with a simple potentiometric devices. So these are some of the advantages of amperometry over other conventional processes. Then coming to some few examples of amperometric titration. So first is the determination of zinc with EDTA. So for this process, the titrant should be 10 times stronger than the Zn plus ion. So 5 ml of zinc ion solution is kept in the titration cell, and 1 ml of cyclohexylamine and distilled water, they are added, and the applied potential is set. Now the solution is deaerated and nitrogen is passed for 1 minute. Then large amount of current will be decreased as the titration proceeds to a small value, and then this process is repeated, and finally the readings are plotted. Then coming to determination of sulfate with lead nitrate solution. So the potential is set, and the reagents that are required are 0.01 molar of potassium sulfate and zero point 0.1 molar lead nitrate, ethyl alcohol, concentrated HNO3, and thymol blue as the indicator. So here the potassium sulfate solution is taken in the titration cell, and the thymol blue indicator is added to it, followed by HNO3, then a red color is obtained. So once red color appears, ethyl alcohol is added to it. Then after that, nitrogen gas is passed into the titration cell and the DMA is connected. So after titrating with lead nitrate, then nitrogen is passed for 1 minute and the reading is noted down. And from the graph, we can find out the exact endpoint of the calculation. So there is also lead, determination of lead with standard dichromate solution can also be done through amperometric titrations. Then coming to titrations with the rotating platinum electrode. So mercury cannot be used as electrode at positive potentials because of its oxidation, and therefore rotating platinum electrodes have been used. So when platinum is used, the achievement of steady state diffusion current is slow, and one has to wait for a considerable time after the reagent is added. So the construction of this electrode, here it is shown in figure 8.15. This is a rotating platinum electrode. First, this has been used for determination of antimony with potassium bromate. So the reagents used are potassium antimonyl tartrate, and that is, to this it is taken in a titration cell, and it is titrated with potassium bromate by setting the standard voltage and then finally the graph is plotted as usual. Then coming to biamperometry or dead stop end point method. So here in amperometry, we use one polarized electrode, which may be either DME or metallic or like platinum electrode. However, uh, the reference electrode that is taken, it is mostly non-polarized in nature. Now in this potential, the potential corresponding to the limiting plateau current is fixed, and I1 is measured as the function of reagent volume. So in the method of biamperometry, a pair of identical metallic or solid micro electrodes, they are used. This method is very simple, and the instrumental setup here, it has been shown in figure 8.16, whereas uh, bimetallic microelectrodes, they have been used. So here, in if both the couples they involved in the titration are reversible, then we get curves like that shown in figure 8.17. Like for example, Fe2 plus solution in sulfuric acid mediated medium titrated with standard cerium 4 solution, it gets oxidized to Fe3. But since we get a plot like it is reversible in nature, and the plot is shown in Enigma figure 8.17. Now, whereas here in figure, if one of the couples is irreversible in nature, then the shape of the curve will be that shown in figure 8.18. Like for example, titration of iodine by thiosulfate. So here the iodine-iodine couple, it is reversible, and the titrant thiosulfate tetrathionate couple, it is irreversible in nature. So what happens here is the titration curve will be as the one that is shown in figure 8.18. We will have if the couple is irreversible in nature. So the equation that is involved here is iodine, it becomes 2I minus, and the thiosulfate here, it changes to tetrathionate plus 2 electrons. Now when the iodine in a solution containing iodide, it is titrated with thiosulfate, the anode will oxidize the iodide ion, and the cathode, it will reduce the iodine, because here we know that the iodide iodine couple is reversible in nature. So as more and more iodine it gets removed from the solution by adding more and more thiosulfate, the current decreases, because there is less iodine available for the reduction at the cathode. Then ultimately at the end point, the iodine is completely removed from the solution, and the current reading will almost be close to zero because of the unavailability of iodine. So after the end point, if more thiosulfate is added, the current does not change. It remains the same because the titrant couple is irreversible and the applied potential is very small. That is why from this equation we see that this point after the end point, it does not change much. Now other examples of such type of titration is titration of azobenzene in dilute HCl with chromium ion. So, in summary, we can say that today we have discussed about the different theories of polarography and amperometric titrations. We have talked about the different advantages of DME, followed by the factors that influence the half-wave potential and the diffusion current. We have also discussed about the amperometric titrations and polarographic analysis. So, with this, we finished this chapter on polarography and amperometric titrations. So we'll begin a new chapter on the next class. So thank you for today.
Thank you, ma'am.